You're here because you want to master nitrogen compounds with a University of Cambridge graduate. Let's begin. If you've made it this far, I have to say, congratulations. You have made it to the final chapter of the organic chemistry module. When you take a look at this final chapter, you will realize that nitrogen compounds are really a class of compounds on its own, and it's pretty unique. The main takeaway from this chapter will be what determines the basicity of nitrogen compounds, as well as some of the reactions of your nitrogen compounds, like your amines and your amino acids. You can download a free copy of my notes in the link below, so check that out, and you can use it to follow my lesson closely as you watch this video. Let's start off with amines. For amines, we've already been covering that in some of our previous chapters, for example our halogen derivatives masterclass, where you can do nucleophilic substitution of your halogen alkane and you can get your amine. So do refer to that lecture if you need a slight recap or if you've forgotten some of the content already. We can also do reduction of your CN group or your nitriles group in order to get your amines. So again, this is also covered in your halogen derivatives masterclass. You can also do reduction of amides to amines. So this is a new one, so I'll be covering it. So if you look at this reaction equation over here, do remember this 4H over here that you have to put in to balance the equation. Under the reagents and conditions of lithium aluminum hydride in dry ether and room temperature, classic reducing agent, you can reduce your amides to amines. You can also reduce your nitrobenzenes to amines. This is a very unique reaction that's covered in this chapter, and is one that is very commonly asked by the examiners as well, so I will really emphasize that you memorize this reaction and the reagents and conditions. So remember to balance your equation with the 6 H's, and the reagents and conditions are SN, concentrated HCl, and heat. Now, for your basicity of amines, you have to look at the number of electron donating alkyl groups that is bonded to your nitrogen atom. And this is because when you have more electron donating groups, you can increase the electron density on your nitrogen atom, and therefore that will make the lone pair on your nitrogen more available and more attractive for donation to electrophiles, thus making your nitrogen compound more basic. So for example, over here, if you look at the order of basicity, you realize that here you have 3 R groups all the way to the left, and therefore it's the most basic. And then you keep going on and on, you have 2 R groups, and then you have 1 R group. So you have lesser and lesser electron donating groups, and you start to have 0 R groups, and therefore the 0 R groups is one of the least basic nitrogen compounds. And then of course, you realize that here phenylamine is actually the weakest base. So why is that? Now this is because the lone pair of your nitrogen is delocalized into the benzene ring, and therefore it's not really available for donation. So this lone pair is delocalized due to the p orbital of the N atom that is having side-on overlap with your pi electron cloud of your benzene ring. A very familiar concept that we've already covered as well in your hydroxy compounds with regards to your phenols. And this would therefore make your lone pair less available for your donation. So do take note that we always keep talking about the availability of the lone pair of your nitrogen atom, and this is the main catalyst or the main driving force of whether you can determine it is basic or not for your nitrogen compounds. And therefore, there are other factors that will also affect your basicity, which I've kind of covered in previous organic chapters as well, so you can refer to those for the full explanation. So you can look at the number, proximity, and the strength of your electron donating or your electron withdrawing groups that affect your electron density of your N atom, and therefore affecting the availability of your lone pair of your nitrogen atom for donation. So these are the factors you have to consider whenever we are determining the basicity or we're comparing basicity between different compounds. Now for your reactions, your amines can undergo nucleophilic substitution. I've already covered this as well in your halogen derivatives masterclass. You can also do nucleophilic substitution with acyl chloride. So over here, this is a new reaction. This is actually a condensation reaction. And here all you're using an acyl chloride that's anhydrous, and it can react with an amine, and under a condensation reaction you'll get an amide over here. And the observation will be white fumes of HCl because it's the side product. Now you can also have electrophilic substitution of your phenylamines. And just take note that your NH2 also has the similar electron donating properties as an OH group to a benzene ring, like your phenols. and it's also twofold directing. So some of the reactions that can occur are like your bromination. So you can use Br2 aqueous, and you can get this multi-substituted product. Again, it's multi-substituted because the NH2 is a activating group, and the observation is you'll obviously see your orange Br2 decolorized, but you also see a white PPT that's formed, which is the product, and you have white fumes of HBr that's formed. Next up, it's important to understand why there's a lack of basicity in your amides. While amides are nitrogen compounds and there's a lone pair on the nitrogen atom, you must realize that the nitrogen atom lone pair is delocalized into the pi electron cloud of the adjacent C double bond O bond. And this delocalization is actually really strong, and even stronger than your phenylamine. So the nitrogen lone pair is really just not available for donation at all, and therefore there's a lack of basicity. And your amides can also undergo some reactions. For example, it can go through hydrolysis. So you can do it in acid, for example with HCl over here, just an example of a reaction. And you can get your carboxylic acid and your amine with a positive charge and a H+. Of course, there's a Cl- over here as well. Or you can hydrolyze it in base. And when you hydrolyze it in base, everything is like in a basic property. So let's say use NaOH, and under heat, you can get your carboxylate anion over here because it's in a basic environment. And you also get your amine because it's also in a basic environment. You can also reduce your amides to amines, which I've also covered earlier as well. So just refer to the earlier part of the notes. Now moving on to your next nitrogen compound, we're going to be talking about amino acids. So you're going to always be hearing about amino acids, especially if you're a bio student, and this is because amino acids is one of the building blocks of proteins. Now, amino acids also have very interesting chemical properties in the sense that you can also form Zwitter ions from your amino acids as well. So if you take a look at a typical reaction of your amino acid, it has a carboxylic acid group and an amine group as well, all in the same compound. And you also have this R group over here, and the different R groups is what makes up the different amino acids. So because it has a carboxylic acid group and an amine group, you're gonna have switching of a H+ from like the carboxylic acid group all the way to the amine group. It's like the acid reacting with the base itself, and it actually forms this very stable Zwitter ion that is shown on the right over here. And this gives amino acids very interesting physical properties. For example, it exists as a crystalline solid with very high melting points because Zwitter ions can form very good ion-dipole interactions with each other. And this also makes amino acids amphoteric in nature because it has an acidic group and a basic group, so it can act as either of them. So what are some of the reactions of your amino acids? Well, because they have both acidic and basic properties, they can react with both acids and bases. It can also form peptide bonds between the amino acids. This is actually what forms your peptide chain and your polypeptide, and this is what gives rise to your proteins later on as well. It's very familiar to you if you're a bio student. Now, this is also a condensation reaction, so just take note over here. And H2O group is going to come out, and what's happening is the carboxylic acid group is going to react with the amine group, and this is what forms the peptide bond. You also form the amide in the process as well. Now, of course, you can also hydrolyze your peptide bond because it's an amide group, and we know that amides can undergo hydrolysis. So you can either hydrolyze it in acidic environments, or you can hydrolyze it in basic environments over here. So that's all for nitrogen compounds. A very quick and simple chapter, and again, the main takeaway that I want to emphasize is you need to know about the explanations for determining the basicity of your nitrogen compounds, and it's especially useful when you're comparing acidity or basicity of compounds, organic compounds especially. And you want to know about the reactions and the reagents and conditions that your nitrogen compounds can go through as well. If you like this content, be sure to hit the subscribe button below so that you can get more frequent updates from my channel. And if you want to enroll in my chemistry tuition class, be sure to hit the link below so that you can book a free call with me, and I'll run through any doubts and clarifications you might need, and also run through your past exam paper for free. And I'll also show you why my chemistry tuition class is the best fit for you. I'll see you in the next lesson.